what we're going to do is, in this situation, for this last little bit, we're going to extend it to what happens when you have more than 2 degrees of freedom. You can extend that theory, the same process can be used to solve any degree of freedom system, an n degree of freedom system. But the problem is anything above 3 degrees of freedom is either very laborious to solve or impossible to solve by hand. Okay? So, in terms of what we're going to do here is we're going to look at 3 degree of freedom system problems. We'll deal with what happens when you've got more degrees of freedom in the next couple of sessions. But for 3 degree of freedom systems, the same process, but there's a couple of things that we need to think about. If we do this, we'll find that the determinant of the mechanical impedance matrix ends up being a cubic equation, not a quadratic equation. Okay? Now there isn't a nice little formula that you can use to solve a cubic equation. So what we do is if you've got a semi-definite system, you know that one of the omegas is 0. Okay? So you don't need to worry about one of them, so that you end up then with an omega 0 times by a quadratic. You can then solve it using the standard equation. And what I thought we'd do is the best way to do this is to do an example. Now I have got slides for the example, but I've decided that I'm going to do it on the board, on the visualizer, because there's a couple of steps that I jumped when I was doing the example and on the slides, and I thought it might help if we go through it by hand. So that's what we're going to do. So here's our example. This is in the notes, so you can not follow if you want to, but I encourage you to do so because I skipped some steps. Okay, so here's our problem. You can see straight away that it's a semi-definite problem because there's no ground indicated in the drawing. None of them are connected to any solid surface. First step, equation of motion. So we can use the quick method, M1, M2, M3, everything else is 0. There's our mass matrix. X1 double dot, X2 double dot, X3 double dot. What's the sum of the masses connecting, so the sum of the springs connecting mass 1 to another mass? K1, yeah? For mass 2, what have we got? K1 plus K2, because we've got those two masses, 2 springs, and then obviously mass 3 is just K2. And then the springs connecting mass 1 and mass 2 together was just K1, so that's minus K1 here. It's symmetrical, so it's minus K1 there. Between mass 2 and mass 3, well, that's going to be minus K2. And there's no springs connecting mass 1 and mass 3 together, so these terms are 0. X1, X2, X3. There's no applied forces, so our value there is 0. We're making some assumptions at this point. We're assuming that the springs are linear, okay, which is a reasonable assumption to make. And we're assuming there's no damping. And so what we do is we make our substitution now. So there's our equation of motion. 2, we find our natural frequencies. So we substitute in xi equals big X I cosine omega t plus phi. So xi double dot is going to be minus omega squared xi cosine omega t plus phi. So I put these into this equation, so we end up with m1, 0, 0. Since m1 plus m2, m1 equals m2 equals m3 equals m, I'm just going to write m, and m. And here, k1 equals k2 equals k, so obviously I can write here k minus k, 0, minus k, 2k, minus k, 0, minus k, and k. Obviously this can drop out. And I can rearrange this equation. We can say k minus m omega squared for the first one. We've got minus k and 0. We have minus k here. We have 2k minus m omega squared minus k, 0, minus k, and k minus m. So this here is our mechanical impedance matrix. So the step we're at now is we've got to solve the determinant of a 3 by 3 matrix. So as an aside, I'll just write it out here. Determinant of a 3 by 3 in terms of A's, A11, A22, A33 plus A12, A23, A31 plus A13, A21. So if you had a 3 by 3 where the terms in the matrix were A, there's the thing here. So that term would be A11, that would be A22, A33, A21, A31, and so on. This equation gives you the determinant of that 3 by 3 matrix. And so what we can do is we can find the determinant of this matrix. This first term is obviously the diagonals multiplied together. So we've got k minus m omega squared, 2k minus m omega squared, and then k minus m omega squared. That's the first term. Done. The second term includes a13 and a31. Well, they're both 0. So we don't need to worry about that second term. This third term also includes A13, so we can ignore that term. This term we've got to worry about because it's got A11, which we've got to think, and then A23 and A32, those two terms. So we have minus k minus m omega squared minus k minus k. So we've got A12, A21 and A33, well that's those two terms and this term, so we've got the same thing again, minus k minus m omega squared minus k minus k, so we've done that one. And here we've got A13 and A31, so again that disappears. So there's our equation. Let's just move it up. So this is our characteristic equation. You can see straight away that it's going to make a cubic because we've got an omega squared here, an omega squared here, and an omega squared there. So obviously those 3 omega squareds are going to make omega to the power of 6, or lambda cubed. Okay. And so we can go through the process to solve this. The first 3 terms I'll leave as they are for the time being. And here we've got a k squared and a k squared, but there's obviously 2 of them, so we have 2k squared, k minus m omega squared. So I'm just going through multiplying out these various terms, okay? You can see straight away on here that and that are the same, so they can disappear. So multiplying these last two terms out, we've got minus 3k squared omega squared. That's that times k, plus k m squared omega to the power 4, plus 3k m squared omega to the power 4, minus m cubed omega to the power of 6. So putting this in order of omega to the powers, we've got m cubed omega to the 6. We've got a minus sign here. Here we've got omega to the power 4 and omega to the power 4. They can add together, so we end up with plus 4k m squared omega to the power 4 minus 3k squared omega squared equals 0. I'm going to divide the whole equation by minus 1 because it makes things easier. So we end up with m cubed omega 6 plus 4k m squared minus omega 4 plus 3k squared omega squared equals 0. So from this equation to this one, I've divided by minus 1. That's a minus sign. And you can see that in each of those terms, in this term, this term, and this term, there is a common m omega squared term. So I'm going to take it out. This is where the trick comes. So this becomes m squared omega to the power 4. This is minus 4k m omega squared plus 3k squared. And if you remember back to your GCSE maths, you can factor that and you end up with so from this we've got omega 0 is 0, omega 1 squared is square root of 3k upon m, and omega 2 squared is k upon m. Obviously, when you square root it, this is what you get. Okay, so this is what we've got in the notes. In the notes, I've actually called this omega 2 and omega 1. Doesn't matter. It's up to you which order you do it in. So we know straight away with the 0th mode, x it's going to be, there's no oscillation between the things, so everything's 1, 1, 1, okay? That's the 0th mode. Don't forget to include that mode when you're dealing with the modes, okay? It's important. So to find mode 1 and mode 2, or the modes when we've got omega 1 and omega 2, obviously we need to use this mechanical impedance matrix, which is up here, and we plug in omega 1 and omega 2 and we find the values. So let's do that. So here's our mechanical impedance matrix. And we'll deal with omega squared is k upon m. So this is actually omega 2. So we've got k minus m, k upon m, minus k, 0, minus k, 2k minus m, k upon m, minus k, 0, minus k, and k minus m, k upon m. And here we've got R, 1, R2, 1, and R3, 1. And the reason why I've called it 2, 1 and 3, 1 is this is the second motion of mass 2 in the first mode shape and motion of mass 3 in the first mode shape. And obviously the other one will be R2, 2 and R3, 2. Because it'll be... Okay, so this is motion mass 1 in the first mode shape. Obviously we're normalising it and saying that equals 1. And so the two other motions are relative to that first mass. Unfortunately, we've got two unknowns, but 3 equations in this thing, so we can solve it. Obviously this cancels with this cancels with this, and this cancels with this, so these are all going to be in terms of k. So here we've got k minus k, so that's going to be 0. Here you've got minus k, well if you divide it by k we have minus 1. We've got a 0 there. We've got a minus 1 here. 2k minus k, well that's going to be k, so that's just 1. Here we've got a minus 1. Here we've got a 0, minus 1 and a 0. So the first equation is minus R2, 1 equals 0. Sorry?
How do you go from the k part to that one?
Yeah, I divide the whole equation by k. Yeah? Because this is basically k times this whole equation. You get that? Okay. So the first equation is minus 1, sorry, let's take the first line, the first row, multiplied by the column, so you have 0 times by 1, plus minus 1 times by R21, plus 0 times R31, equals 0. Okay? So obviously the only term in there is this minus 1 times by R21, so you have minus R21 equals 0, therefore R21 must equal 0. Okay, makes sense. Let's take the middle line. We've got minus 1 plus R2, 1 minus R3, 1 equals 0. Well, obviously we can stick in 0 in here, so we have minus 1 minus R3, 1 equals 0. Therefore R3, 1 must equal minus 1. So x1, which is the first oscillatory mode shape, we have 1, 0, minus 1. And we repeat this process for 3k upon m being the omega squared. And so we can go through the process again. K minus 3, m, 3k upon m, minus k, 0, minus k, 2k, minus 3mk upon m. Okay, so there I've stuck in 3k upon m. Obviously the m's cancel and we can divide by k again. So we have k minus 3k, so this is obviously going to be minus 2. Minus 1, 0, minus 1, 2k minus 3k, minus 1, minus 1, 0, minus 1, k minus 3k minus 2. So taking the first line, we've got minus 2 times by 1, minus 1 times by r2, comma 2, and 0 times by r, comma 3, 2. So we have got minus 2 minus r2, comma 2 equals 0. Therefore, r2, comma 2 is going to be minus 2. And then to find the third one, we can either use the second line or the third line. Well, let's use the second line for no reason whatsoever. Minus r2, comma 2, minus r3, comma 2 equals 0. We know r, comma 2, comma 2 is minus 2, so we've got minus 2 plus 2, sorry, minus 1 plus 2, which is 1, minus r3, comma 2, so r3, 2 must equal 1. And so x so we've got omega 0 is 0, omega 1 so we've got our 0th frequency is 0, omega 1 we said is 3k upon m, and omega 2 we said is k upon m, okay? Square root of both of those, obviously. Omega 1 is root 3k upon m, omega 2 is root k upon m. And then we've got the three mode shapes. Obviously with omega 0, we've got 1, 1, 1. All three masses will move with no oscillation. They'll move all in relation to each other. Mass 1 moves by 1, mass 2 will move by 1, and mass 3 will move by 1. For the case when omega is root 3k upon m, you've got mass 1 and mass 3, they will move together, but the middle mass will move in the opposite direction by twice the displacement. Okay, so you have the two masses moving backwards and forwards, and the one in the middle will move in the opposite direction. In this case, when omega squared is root k upon m, sorry, omega 2 is root k upon m, you have this mode shape where you've got mass 1 and mass 3 are moving opposite directions but by equal amounts. The mass in the middle doesn't move at all. There's your three mode shapes. Okay. When I did this in the notes, obviously I said that omega 2 was k upon m, so that should be x2. Okay, and I said that omega 1 was 3k upon m, so that's x1. What I've written down here is correct. That relates to that, that relates to that, and that relates to that. Had you done it the other way around, it's the same answers, okay? No detriment. So what's in the book is also correct.